We want to talk about artificial intelligence. So Andrew Chatman is going to talk about that as senior staff engineer here in New York, right? Working on self-driving cars. Now, the only problem with artificial intelligence is the moment we ever describe something that's more or less working, many of you will claim that it's no longer artificial intelligence. So I don't know that this is artificial intelligence since your stuff is more or less working to a very large degree. So in any case, we think it's artificial intelligence. And then the other theme that we're talking about is mobile, and you're going to hear about mobile voice work, which is very significantly done here in New York, and Johan Schoklik will be discussing that next. So without further ado, Andrew.
Thank you. Hi, everyone. I'm here to take the magic out of self-driving cars, which I guess is no longer AI. So in case you haven't heard, we at Google have developed a fleet of self-driving Priuses that we've been taking through public roads in California and bits of Nevada. Unlike some other self-driving vehicle efforts, we always have a human in the driver's seat. Often we have a second person in the passenger seat to make sure that nothing weird goes on, but we've been driving them on real roads where you experience all sorts of random stuff. So to go back a bit, research into self-driving cars started in the 80s and 90s, but it got its first shot in the arm in 2004 when DARPA, the research wing of the military, sponsored the Grand Challenge. The Grand Challenge was a 132-mile race through the Nevada desert in which various teams, mostly from universities but some from industry, developed driverless vehicles which were supposed to drive through the desert and complete this 132-mile course, which they had not seen before. Now, in the first year of the contest, the winning team made it out of 132 miles, a bit over 7 miles before it ran into a ditch and its tires caught on fire. Not the result DARPA was hoping for. They ran the contest again the second year, and all but one of the teams entering made it farther than that 7-mile goalpost set in the first year, and 5 of the teams completed the entire course. The first place team was from Stanford, and second and third were from Carnegie Mellon. Yeah. 2 years later, DARPA ran a slightly more interesting challenge called the Urban Challenge, in which they set up a simulated suburb in an abandoned military base and had a set of autonomous vehicles and a set of chase cars driven by trained drivers driving around in a simulated environment. This time, Carnegie Mellon won. Stanford came in second. And there was a minor fender bender, but otherwise it was a very strong start for driverless vehicles.
They couldn't find anybody to be pedestrians in that
Yes. So there were no pedestrians in this, and there were no traffic lights. There were stop signs, and the cars did have to interact with each other and with manually driven vehicles. After that, DARPA abandoned the project and moved on to other contests. They had sufficiently jump-started this technology that they could move on. And research continued, but it didn't really have the impetus that it had when the DARPA challenges were standing in front of us. And that's where Google came in. So Google hired the people from both Carnegie Mellon and Stanford, who are now at Google. And we've been working on this project for about 2 years now. And the question we get asked a lot is, why is Google doing this? So there are 2 parts to that. One is, why should anyone do this? And the answer is because it's really important, which I'll get to in a bit. And the other question is, why is Google qualified to do this? And this is a large-scale computing problem. We have a lot of experience, as John just told you, with large-scale computing. And we also have a lot of experience with geospatial data. Our maps, Google Earth efforts are enormous, and they're quite related. A lot of the people who work on this project used to work on Street View and Google Maps. Google also wanted to set up something that we would develop with urgency and that we would develop safely. The DARPA challenges really provided a lot of motivation for people to get this done quickly, and not just as an abstract research problem, but as something we really wanted to do for the world. And Google's trying to recreate that. So why is this important? The main reason is that a lot of people die from auto accidents. It's over 30,000 people a year. The auto industry and the government has done a great job in reducing the number of fatalities per mile driven in recent years, but they're reaching the limits. seatbelt education campaigns, the development of side impact airbags have done a lot for crash mitigation. If you're going to have a crash, we would like you to survive. But at this point, it needs to turn to crash avoidance. And the auto industry is looking at that, but you really need autonomous cars to avoid the problem completely. And we're certainly not claiming we can do that today, but that is the eventual goal. Auto fatalities are also the leading cause of death for young people. So if you look at this in terms of the number of years of life lost, it's a much bigger impact than if you just look at the number of fatalities from auto accidents.
How much was that US, right?
Sorry?
How much is that just for the US?
The numbers are just for the US. It's actually worse in a lot of developing countries. So I think it's something like 1 or 2 million people per year die in auto accidents. So a pretty tragic loss of life. So the other reason this is important is that we waste a lot of time in cars that we could otherwise be doing useful or not useful things. Plenty of people enjoy driving, but I don't know that a lot of people enjoy their daily commute stuck in traffic. If you could be spending that time reading a book, watching a movie, taking a nap, a lot of people's lives would be greatly improved. So this is seriously important stuff. There are two approaches to autonomous vehicles that have been taken so far. We can call it the infrastructure approach and the non-infrastructure approach. So up there is Boss from Carnegie Mellon, and that exemplifies the non-infrastructure approach. That was for the Grand Challenge. They had no idea what was out there. They were put in the Nevada desert and told, you must pass through these waypoints and reach this finish line. No idea what's going on. You have to drive very conservatively because there could be a giant rock in front of you. The road isn't even paved. This is the bare minimum of infrastructure that you could have and still be able to drive a car. At the other end of the scale is something like the personal rapid transit system at Masdar, the city being built in the United Arab Emirates. This is a lot of infrastructure. They've essentially built an underground road system in which autonomous vehicles navigate based on a sensor network built into these underground roads. And they're able to take you from point to point. This is great as far as it works, but it's extremely expensive to build this out. It's essentially constructing a subway system. And it's not practical to build this out across the United States if we hope to get autonomous cars done anytime soon. So here's Google's robotic Prius. So we've got a bunch of external sensors, the most important of which are probably the radars, which can give you distance and velocity measurements, and the LiDAR, the laser rangefinder that you can see on top of the car there. So that's 64 beams of lasers spinning in a circle at 10 rotations per second. We get about 1 million laser readings at a range of about 100 meters per 1 million points per second. In the interior of the car, we have a couple of more sensors. The important ones there would be the cameras, which we use both to get situational awareness after the fact and to do traffic lights. The laser and the radar are great, but there's really no way to tell if a traffic light is green other than looking at it with a camera. So we also interact with the car using a drive-by-wire system that actuates it as if it were a human driver. So it's not literally pressing the gas and the brake, but it is hooked in just below that and acting that way. So people ask, how do you interact with anti-lock brakes or the stability control? And the answer is that we sit on top of all of that and interact with the Prius as if we were pressing the pedals or steering the steering wheel. And there's a giant computer in the back. All right, so I'll describe the software stack kind of briefly. At the base level, you've got a position system. We know which direction we're facing. We know roughly where on the planet we are, and we know kind of a Cartesian distance that we've traveled. So we are now 3 meters east from the last time you checked. On top of that, we have a localization system. Now, GPS is really inaccurate. On a good day, a regular GPS will be about 1 meter of error. On a bad day, it'll be 20 meters of error, and that's worse when you're surrounded by mountains or if you're in an urban canyon like out on 9th Avenue. And so we have a laser localization system which examines a map and examines what the laser can see, aligns those two, and tells you, okay, I'm pretty sure that you are in the left lane and you are 3 meters from the crosswalk, and you should act accordingly. On top of that, we've built a symbolic graph of what we think the road looks like. That tells us that this blob on the road is actually a crosswalk, and you should treat it accordingly. That if you want to go from this lane to that lane, you need to stop at this stop sign, yield to the people in this crosswalk, wait for that traffic light to turn yellow, or green. Wait for it to go yellow, then just blink. Yeah, no. Wait for it to turn green, and then you can continue onto this road, and don't go off that other road because it's going in the other direction, that sort of thing. On top of that, we have a perception system, which turns the raw measurements from the radar and the laser into symbolic things that the higher level software can reason about. You know, it's not enough to know that there's a blob sitting there in the road. We need to know that that blob is a person or a tree or a car and how they're going to react so that we can, you know, behave accordingly. Once we have all of that information, we turn that into a trajectory, which will take away everything else. The trajectory tells us where we want to go, how we want to steer, and what gas and brake we need to apply. In the end, that's all that matters. That's the only reason we're bothering with all of this road network, where we are, what else is there. It's to tell us what gas and brake to apply, where to steer, and all that stuff is also used in the user interface, which is its own separate problem. But creating a trajectory is the important part. Let's see. So I mentioned we build maps. We build several different kinds of maps, which all get kind of stitched together in the end. We build, in the top left, you can see we build an intensity map, and that tells you how reflective are different surfaces on the road. So you can pretty easily see it looks a lot like a black and white satellite image, which we build from the intensity returns we get from the laser. We also build an elevation map. On the top right, you can see that's a map of Lombard Street in San Francisco, which is a challenging elevation environment. Second steepest road in San Francisco. On the bottom left, you see a staticness map that tells us how likely a part of the world is to move. We need to tell the difference between someone waiting in a corner and a tree that happens to be planted at a corner. You need to yield to one, and the other one is not going to move. And then in the bottom right, you can see our symbolic graphs that we've laid on top of the raster maps, and those are created in a semi-automated method, but there's a lot of human effort that goes into laying those out. So at a basic level, the way we build the intensity and elevation maps is we take all of the laser returns and we plop them down on a map and we paint it. And that actually works about like you're seeing now. This is highly stylized. We actually use a giant MapReduce to do all of that, but here's the pretty picture version of it. And that seems fairly straightforward. Unfortunately, if you just do that in the naive way, you'll end up with maps that look like this. And I don't know if you can see it, but they're double images of almost everything in that map. The crosswalk, there's another crosswalk slightly, maybe a meter to the left. The arrows you see there maybe moved northeast or northwest a little bit. And the reason that happens is because GPS is terribly inaccurate. If you had differential GPS everywhere, then yeah, you could take care of this problem, but that's, again, an infrastructure problem. We don't want to have to deploy differential GPS base stations all over the country before we can do this. So what we do is we find out image alignment between the two passes. What you saw there was we had passed through the intersection one way and the other way, and the GPS was slightly off, and if you paint it, it looks like a mess. So what we do is we take the two images that you had, we blur them, we turn those into a gradient, and then we'd run a convolution on them to figure out how they line up. And once we have that ground truth, we add those as constraints into a SLAM optimization problem and squish and stretch the trajectories until everything lines up in a realistic way. And then we paint all of the pixels onto the map. Separately, we build an elevation map, as I mentioned. And this is essentially the ground plane of the world. The main reason this is important is that if you see a laser return from 50 meters in front of you and 2 meters up, you don't know if that's the ground or not unless you know how high the ground is, both where you are and where the laser return comes from. This is tricky because as bad as GPS is in the plane, it's really bad in elevation. You need to see about 5 satellites before you can get a really good elevation reading. Often it's off by 100 meters or more. So the intensity maps we build go into laser localization. What you can see, that rectangular box is where the GPS thinks we are. The red blob is a particle filter estimation of where we think we are. Now, as you can see, the GPS is biased severely to the right, which means that if we were trying to drive this, we would bias to the left, and we would be driving on the curb, which would be pretty bad. This system works well enough that we can tell within about 10 centimeters where on the map we are. So I mentioned perception is an important system we have. The original approach we took to perception is essentially to do clustering of laser points. If we see a bunch of points above the ground and they look like they're a rectangle, then that's probably a car. Clump them together, and you also need to do tracking, that the blob we saw at time t is the same blob at t plus 1, therefore it's moving at this many meters per second, and so on. And that works really well in a lot of environments. It's certainly enough for the desert challenge because nothing moves. It's also enough for the urban challenge because it wasn't very dense traffic. There aren't that many blobs to keep track of. It does not work very well when you're driving in real environments like we've been doing, because in a complicated intersection, the nearest neighbor algorithm is going to associate things in the wrong way and whatnot. So on top of that, we layer hypotheses about where we think things are going to travel based on the road graph. That we know you're only allowed to go straight or turn left from this lane, therefore it is likely that the car is doing one of those two things. We form multiple hypotheses about these. We incorporate observations and eventually eliminate one of the hypotheses. And so you can see these trails represent where we think things are going to pass. And you can see in the top left corner, that's a fairly busy intersection. And if you were just doing clustering and nearest neighbor, you would get the wrong answer. It's not enough to know that there's a blob. You need to know what kind of a blob it is to know how it's going to behave. You need to know if it's a bicycle, a person, a car, or a tree. And so we have various heuristics and a bit of machine learning to identify that this is indeed a pedestrian and it is going to behave in a somewhat erratic way, but is probably going to try to cross this crosswalk. And in California, you're required to yield to people in crosswalks, so we do that. So I mentioned the urban challenge did not have traffic lights, but the real world does. So we have to deal with those. This is a computer vision problem. You would think it's fairly easy. These are extremely stylized blobs of light. Should be totally easy. But it turns out if you're in the real world and looking in arbitrary places with cameras, there are a lot of blobs that look a lot like traffic lights. One problem we had was an ad for Corona that had a lime. Looked a whole lot like a green traffic light. But turns out we know where all of the traffic lights are. And so we use that information, and we know exactly where in the camera image we need to be looking for this light. And so in this case, we've highlighted where we think the traffic lights might be. We identify the blobs, use computer vision to figure out what color the lights are. Then we incorporate the road graph to figure out which elements of the light we need to obey. In this case, we're going straight, and so we can ignore that red light off to the side. A nice thing about traffic lights is that they're incredibly redundant in the real world. In this case, there are two green lights telling us we need to go. If we saw either of those, that's enough to tell us that you're allowed to go through the intersection. And so this doesn't need to be 100% foolproof. But when it does fail, we pretend that all the lights are red. We also treat yellow lights as red because we're not seeing a green light. So here's an example of what we're able to do in terms of high-speed driving. We would not normally be driving like that. This is on a closed course. Normally your hands are over the wheel and your foot is near the gas or the brake. But we're able to drive extremely precise maneuvers through this course, which we set up and made a map of.
Is it significant that some of the cones look like they got
We do periodically nick some of the cones. You know, you drive the trajectory, you move the cones in enough to be exciting, but you know, every once in a while you'll nick one. So motion planning. So at a high level, we have a route planner, which is a lot like Google Maps driving directions, which tells you need to take this road to get here and turn left, whatever. Below that is a motion planner, which at a basic level is following the idealized curve of the road. We've laid out a road graph that tells us how you need to move, and we follow that. Unfortunately, the real world is not so simple. We can't just follow these idealized curves or you will run into a giant truck. And so on top of that, we have to nudge and swerve around objects. And these are real-time modifications to the idealized curve so that we can get through tight obstacles. So here's a case where we're trying to get through a toll booth, which is extremely narrow, and the idealized trajectory would have gotten us too close. And so the trajectory gets nudged to one side. A separate issue is lane changing, which is an extremely social behavior. You would think that you can just plan this using some kind of generic motion planning algorithm, but people react to us, and you have to act sufficiently aggressive and also polite at the same time. And we try to find a gap and move into it. And so we ought to see, there we go, an executed lane change. And that one was fairly easy, but we're able to do these in dense traffic and also merge onto and off of highways. An even more social issue is a four-way stop. We all know the rules for handling a four-way stop, and it turns out no one follows those at all. And so we initially follow the rules. We stop, we wait for our turn, we yield to everyone who's going through the intersection. No one manages to give us a slot to get in. Eventually, we start to get impatient. We assert ourselves by moving slightly into the intersection. No one is giving us a shot at all.
That's when we turn on the 50
There,
megawatt laser.
now we go. No one's letting us go. Yeah, and then we go. Yeah. So there are a lot of intersections where if you follow the rules of the road as laid out in the DMV handbook, you would never get through the intersection. So what have we done so far? We've driven 160,000 miles of mostly California roads, on public roads. That's obviously not all in a row, and it's on multiple cars. We've driven 100 very challenging stretches of road without touching anything. We didn't do it on the first try, but we did it. So there's an example path there of the worst possible way to get from Silicon Valley to San Francisco. That took 4.5 hours, and it was extremely challenging. But we've done 10 of those routes to demonstrate that we can handle extremely complicated situations. Our map so far is fairly large, but it's certainly not the entire U.S. So here's something we don't talk about a whole lot, but we've been experimenting with lower cost sensors and lower speed driving. The Prius is the third most expensive part in that robotic Prius. So obviously a hefty price. But we've been experimenting with lower cost sonar and other types of vision algorithms to have truly autonomous golf carts, which can drive at very low speeds with lower stakes. Driving is really hard, and weird things can happen. We've still got some things we need to work through. The bug on the windshield is a kind of quintessential problem where, yeah, everything looks good, the sensor's working, but you're not getting any useful information out. Weather is also a big problem. We've done a good job with rain, but snow we have not even attempted yet because the laser is going to act really weird. And then people just do stupid stuff. So here's what's supposed to be an off-ramp, and someone comes barreling onto the highway in the wrong direction at 30 miles an hour. And teaching a computer to deal with that is going to be very hard. I'm not sure what I as a human would have done if I came onto them at a closing speed of 90 miles an hour. And yeah, so that's the self-driving car project at Google. I don't know if we have time for any questions or not, but yeah. All right, 2 questions. Yeah.
Can you say something about which of the data sets you're going to compute offline and which ones are going to process on the car?
Right. So what do we collect offline and online? We have a map of everything that's not moving. So this is the idealized what the world looks like, where you would drive if there was nothing moving in the world and there were no parked cars or anything. That's all done offline. We load that onto the car, and then the job of the onboard software is to figure out how is the world that I see different from the world that I expect, and then react accordingly by nudging slightly or swerving or waiting for a traffic light. Yeah.
Talk a little bit about the legislative and regulatory aspects of actually having these cars on the road. What the obstacles are there?
So the question is about the legislative and regulatory aspects. I don't know that I can say too much about it other than that so far our understanding is that this is treated like cruise control, that the human in the front seat, no, it is, right? This is the human in the front seat is in charge of the vehicle. It is their responsibility not to run into anything. And we're obviously treating safety is a very big issue. We know that if we screw this up, this could be a very big setback, not just for us, but for robotics in general. And we're treating it very seriously. But our understanding is that this is treated like cruise control. So, all right, one more. Yeah.
Does your system learn that, for example, does it take the LiDAR information simulating while you're driving in a car like that with what you learned before?
So the question is, to what extent do we learn based on what we're seeing and incorporate that into what we've seen before? We do some amount of learning. It's not as automated as we would like. We have various regression tests and suites of things, and we incorporate new data into them. But currently, we're producing more data than we can reliably use for learning. It's an open issue that we're working on, but certainly, if we notice that the world is different, totally different than we expected, we do incorporate that. So that's probably all the time we have, but for questions. But thanks, guys.